Welcome to the video for C2.2.6, where we're going to look at giant covalent structures. So you'll hopefully recognise the word covalent from previous lessons where we've looked. So in the last lesson we looked at simple covalent molecules where you've got covalent bonding between non-metals, but they made small simple molecules. So in giant covalent structures, which are sometimes called macromolecular substances, you've got one big massive molecule rather than lots of small ones. So before we start, there's a question for you to think about. So based on what you already know, what similarities and differences can you come up with between carbon dioxide and silicon dioxide? So have a think about where carbon and silicon are on the periodic table. That might help you a bit. Okay, so pause the video and then we'll talk through a few examples. Okay, so hopefully you've come up with some similarities and differences. So the obvious one is that we know carbon dioxide is a gas, and you can see by the picture that silicon dioxide is a rock, so it's a solid, so there's a difference for you. If you look at the name, they're both dioxides, which means if you look at the chemical formula, it's got O2 in it to show that there's two oxygens in there. And if we've looked in the periodic table, we've hopefully found that carbon and silicon are both non-metals. And in the first lesson of this unit, we looked at the idea that if you've got oxides of non-metals, they're going to be acidic. Now, it's not quite that simple with silicon dioxide because it doesn't really dissolve in water, but in theory, it would be acidic. So today's lesson, we're going to look at the structure and bonding in giant covalent structures, as opposed to the last lesson where we're looking at simple covalent compounds. So first keyword that we need to be introduced to is something called allotropes. So an allotrope is where you've got different forms of the same element. So the main one that you need to know about, which we'll look in more detail in a later lesson, is carbon. So carbon, you met diamond, you know about graphite, which is the lead in the middle of your pencil. You may have heard of Buckminster fullerenes or nanotubes. These are all allotropes of carbon. So it's still carbon. So if you looked down at each individual atom, they're all going to be the same because they're all carbon. But because they're arranged differently, they're going to have different properties. So before we start, we're going to need to think about these questions. So pause the video and see if you can answer these questions. Okay, so hopefully we can recognise from its position on the right-hand side of the periodic table that carbon's a non-metal, and therefore it's going to form covalent bonds if it's reacting with other non-metals. So carbon, because it's in group 4, doesn't really do ionic compounds. So we're going to expect, based on what we've previously done in the last lesson, we'd expect that carbon will form small molecules, and they're going to have low melting and boiling points because of the weak forces between those molecules. Okay, so we might have done last lesson, I can't remember, we might have done carbon dioxide as an example of a simple covalent compound. So we're going to look at something a bit different. We're going to look at carbon by itself now. So just to recap what a covalent bond is. So a covalent bond is where it's a pair of shared electrons. So here's chlorine as an example. So each chlorine atom has got 7 electrons in the outer shell. Remember, they want to get a full outer shell, so each one wants to gain 1. And because they both want to gain, they have to share to get this. So those overlap. Now, I don't really, although I'm giving you this diagram, I feel like the overlap between the 2 chlorine atoms should be bigger, so it should look a bit more like a traditional Venn diagram. So the pair of shared electrons that are being shared between the 2 chlorine atoms are the covalent bond. Okay, and covalent bonds are made when non-metal atoms are sharing their electrons, and you get 1 electron from each atom is shared to make a pair. And this is done, as I said before, to make the full outer shell. So if we look at another example on the next slide. Oh, sorry, before we do that, so last lesson we looked at how to draw covalent bonds. So we can draw them as a line. So if we were to draw the molecule of chlorine, it would be 2 chlorine atoms with a single line between them, and that single line represents a covalent bond. Here's a more complicated example. So this is ethane, which has both carbons and hydrogens. So each of those lines is a covalent bond. So we're going to look at carbon now. So carbon is in group 4. And we should hopefully remember that the group number tells us how many outer shells outer shell electrons that an element has. So if we look at carbon, it's in group 4, so we should have 4 electrons in the outer shell. So if we look at methane, which is a compound, so this is a simple covalent compound. So it's got 4 electrons in the outer shell, and then we need 4 hydrogens. And each of those hydrogens overlaps to give us our methane compound. Okay, so you've got the molecule CH4. Each hydrogen shared 1 electron with the carbon, which has then shared 1 back. So you've got 4 pairs of shared electrons for the carbon and 1 pair of shared electrons for the hydrogen. So it's got 4 covalent bonds. So if we were to draw this out as a displayed formula with the lines, we'd get this. So you've got carbon in the middle, and the carbon goes to each hydrogen atom with 1 covalent bond. So it's got 4 covalent bonds in total. So if we're to look at diamond, so diamond is a big molecule of just carbon. So if I take 2 carbon atoms, each one wants to gain 4 electrons. So if I have 2 carbon atoms and I overlap them, then each carbon atom has now got 1, 2, 3, 4. It's got 5. Okay, so there needs 3 more. So if we take the one in the middle, I can add another carbon to that side and overlap. And now the carbon in the middle has got 6, so it needs to overlap 2 more. Okay, so if we look at that, this carbon in the middle has got, if I can get my pen to work. So the carbon in the middle has got 1, 2, 3, 4 pairs of shared electrons, so it's got 4 covalent bonds. Whereas this carbon here has got 1, 2, and it's got 3, 4, 5. So the ones on the outside have only got 5 electrons, but the one in the middle is now happy because it's got 8 electrons. So you'd have to keep growing this. So you'd then have to have another, so if we had another carbon atom here, overlapped like that, if you excuse my dodgy diagram, it's not really overlapped, it should kind of go more like that, shouldn't it? So you then have 1 from there, 1 there, 1 there, and 1 there. So now this one has got 6 electrons, so you'd have to have another one there and another one there. I'm really sorry about the quality of my drawing. Okay, so basically it's got to keep going infinitely outwards because each carbon needs 4 covalent bonds. So if you have a lump of a diamond, then these covalent bonds go out from one end of the molecule to the other one. Okay, so it keeps going throughout the whole molecule. So every diamond is just one big molecule. So to recap, covalent bonds form between non-metal atoms, and this diamond is an example of a giant covalent structure, which is a giant covalent lattice of atoms joined together by covalent bonds. So we've met the word lattice before for ionic compounds. So you can, as well as having an ionic lattice, you can have a covalent lattice. And other examples that you might need to think about are diamond, graphite, and silicon dioxide. And as I said, in a later lesson, we'll look at diamond, graphite, and nanotubes and Buckminster fullerene. So first task for you to do is copy down the tasks, the sentences on the left, so the statement about their properties, and then match that up with the reason for that property. So have a go at that, pause the video, and then I will go over the answers. Okay, so they have very high melting points, links with this one. So that's number 1. So there are many strong covalent bonds, so a lot of thermal energy is needed to break them. They're very hard. The reason for that is that there's many strong covalent bonds which are hard to break. So we talked in the last lesson about covalent bonds, and that in simple covalent there's weak forces between the molecules, but in this case there is no between molecules, so it's only the intramolecular forces, the forces between the molecules, these covalent bonds, that are important. So Apart from graphite, which we'll look at in a later lesson, they do not conduct electricity, and that's because there's no delocalized electrons. So there's no charged particles which can move. So there's no delocalized electrons, there's no ions, there is no charged particles which can move. And in the previous lesson, we looked at the fact that current is a movement of charged particles. So if we don't have charged particles that can move, we can't have a current. So that leaves they are insoluble in water, which is this one here. So there are many strong covalent bonds, and they're weaker than the bonds that would form between water and the individual atoms, so they don't dissolve. So some exam questions for you to have a go at. So which of these substances has a giant covalent structure? So pause the video, write down the answer, and then we'll check it. Okay, so carbon dioxide, simple molecular, that we use that as an example, so simple covalent or simple molecular. Magnesium oxide, so magnesium is a metal, and oxygen is a non-metal. That's going to be an ionic compound. Sulfur dioxide is a simple covalent. And then silicon dioxide is what we had on our starter. That's a giant covalent. So D is our answer. Okay, last exam question. So this is a summary of all the previous lessons we've looked at. We haven't looked at metallic in bonding in detail yet. We'll look at that in next week's lesson. But you do know the properties of metals. Okay, so pause the video and then I'll go through the answers. Okay, so hopefully we've got metallic is malleable and ductile. Ionic's been done for you. Simple molecular is going to be gas or liquid at room temperature, and giant covalent is going to be our high melting point. Okay, right, so let's revisit starter. What can you add to this now that you couldn't at the start of the lesson? Okay, thank you for listening. See you next time.